the RCSB data bank, and then download the structure directly from the source. Or you can also type in something that is part of the title of the PDB, which I will do now. So I will just type in gefitinib, and I get a list of every PDB structure that is officially available that contains gefitinib in the title. I will just randomly select the first one, click on it, and what happens now, SeeSAR accesses the database and downloads the PDB directly. The first thing that SeeSAR asked us is actually to select a compound or a ligand inside the complex. This step is necessary because we need a ligand to define the binding site. If we don't have a ligand, this step is actually skipped, but we can do it subsequently, which I will show you now. So let's check our compounds. We have gefitinib as the first compound here, and then we have another crystallization fragment artifact here. But since you would obviously like to work with our compound of interest, you just select one. We select our compound here, and then confirm our selection with the apply button. What you will notice now that some residues have popped up in this area, also including water molecules. This is part of the binding site definition. Everything that is displayed now is also part of the binding site. If you have also other ligands in close proximity to your compound of interest, they will also become part of the binding site. This is especially interesting if you're working with structures that contain a cofactor like heme, or I don't know, ATP or ions. Anything in close proximity to the ligand, 5 angstrom, will become part of the binding site, and we will also consider doing subsequent steps like docking and compound evolution. The first thing that we will do, you will notice that the ligand is gone, but it's not completely gone, it's just not selected. To select your ligand, you have to click here, and it will pop up in 3D and also in 2D. Before we start, I would like to introduce you to the settings of SeeSAR. The first thing is, if you have any questions towards SeeSAR, what's new in the version, you will notice the speakerphone here, and if you click on it, you'll be actually led to the changelog of SeeSAR, where you can see what happened in the last release, and also you will be also presented with the latest additions to the software as a YouTube video on our website. The next button is the help button. So every time you are inside a mode and you feel not completely confident in what you're doing, you can just click on the help, and then you will get a nice overview explaining how you can do things. You can also browse for different contents like the filter panel and so on and so forth. There are also additional links to the beginner's guide of SeeSAR, tutorial videos on our YouTube channel, and an online help section, and so on and so forth. In the settings, in the system part, you can work with SeeSAR's settings, which includes calculations. Calculations is actually everything that we do once something happens inside a mode. So every time you create a new ligand, you can decide if you would like to spend additional time on calculating the predicted binding affinity, the H-bond network, intra and intermolecular clashes, as well as the torsion quality and Optivium properties if you have an Optivium license available. Just by toggling those buttons, you can decide what happens automatically and what happens not automatically. So this is kind of like a pretty nice way to decide when you would like to know some stuff and just not invest computational resources when you do something. In the Inspirator system settings, you can decide which vCore indices and FastCore libraries you're using. We can talk about this later, but this is basically where you can add additional data sets to work within the Inspirator mode. The StarDrop button here connects you to Optivium's StarDrop functionality. So if you have both licenses, it's pretty nice to work on them in tandem. There's also the setting to work with a proxy server if it's part of your computational environment, and also system log if you face any difficulties, bugs, things you did not expect. This is where you can look up stuff to send to us so we can take a look into that. Let's discard our changes. for the time being. Appearances is actually one of my favorite windows. So this is where you can decide the background color of your 3D representation. So you can set a nice Sahara style setting or something dark bluish if you're under the underwater mood. But I will just go with the plain white motif as of now. In the layout settings, you can decide where everything should be presented. So sometimes it's kind of like convenient if you would like to have something at the bottom or on the left side. You can also dock out the windows to distribute them manually on your desktop. We support 2 different teams, the dark team, and for the light-hearted, also the light team. So depending on the mood, you can play around with that. With the label size, you can also increase and decrease the sizes of your labels. I will talk about this in a minute. And also, good news to everybody, we also support color blindness. So if you cannot differentiate between green and red, you also have the possibility to turn green into blue, which helps you to identify the colors better. Utilities is pretty nice. So this is where you can always go back if you lost your compound, like in this case, it's too far zoomed off. And if you want to zoom back on your compound, you can just use utilities. Oops, sorry. You can just use utilities and then zoom on your compound, but you can also use the hotkey spacebar. So zoom in, I will hit the spacebar, and now I'm back on my compound. Next nice feature is the screenshot utility. You have the possibility to export PNG files here. You can select the density of your figure, 300, so kind of like the most common setting used for publications, for figures. You can also adjust the size of your image if you would like to, especially very nice if you're doing some visuals for presentations and or the website as I do. And you can also set a background color to transparent, which is also very helpful if you would like to be creative with what you're doing. Another feature that I really, really love is the export 3D scene, but I will show you later how to use this in the most efficient way. The next thing is the show label part, which is also, if you zoom over a particular entry, you will also see the associated hotkey, like show label. I will now again zoom over it. So if I use this one or the L hotkey on my keyboard, I can label things in SeeSAR accordingly. And if the sizes of the text are too big, I can just decrease it or increase it with the appearance label size option. If I don't want to see them, I can just turn them off. So basically, and the good thing about SeeSAR is you can actually measure everything. You can measure distances with the D hotkey or just clicking on the actuator there. And you receive also the distances between 2 heavy atoms. You can also measure angles with A. See? You can also measure torsions, like in this case, and so on and so forth. Now, we are approaching the scientific part of SeeSAR. You can also visualize quite a lot of things in SeeSAR. One of the most prominent features is actually the height coloring. So if I go in on my compound now, you will notice that my compound carries a lot of spheres on the heavy atoms. And those spheres are actually indicators of how much those heavy atoms contribute to the overall binding affinity. So if I now use the L hotkey for labeling, I can now click on this little nitrogen down there. And what it will tell me is actually the height estimation for the contribution of this particular nitrogen here. Height stands for our scoring algorithm. Height stands also for hydration and dehydration, and this is what we calculate. We calculate what happens to the ligand and the receptor or the target structure once they meet each other. So basically, this nitrogen receives a penalty because it gets desolvated, because nitrogen wants to be in water. and this penalty is 6.8 kilojoule per mole for the ligand part only. Yet, since this nitrogen is now in another environment, namely the surface of the receptor, it can form interactions, and therefore we get a free energy back, namely 8.4 kilojoule. So what HIDE does is actually it compares the contributions of atoms and receptor exposed to the solvent, and now after the binding event, and therefore we can also have to obviously calculate the same thing for the receptor, and by ranking up those numbers, we end up with a positive contribution of 3.4 kilojoule per mole, which is an increase in binding affinity. So therefore, this nitrogen is now more happier because it's in the receptor binding site than it was before exposed to water. Now, maybe to give you another idea, maybe this little fella here, this oxygen here doesn't form any worthwhile mentioning interactions, yet the desolvation compared to water and the environment here, we get a little bit of feedback. But most importantly, since the receptor here, and you can also see which residues are actually considered, since we now strip off water molecules from this lysine here, which is lipophilic, we get a 1.7 kilojoule back and therefore have an increased binding affinity. So this isn't the only thing that we can visualize. You can also visualize the torsion coloring, pay close attention to the ligand. And if I turn on the torsion coloring, you will see that the bonds are weak colored. And this is actually very interesting because this is how we assess molecular strains within the receptor and the target, within the ligand, sorry. What you can see here is actually the arrangement of those 4 heavy atoms. And if you measure this one, we will see that this is a histogram for a distribution that is based on actually the PDB itself. And you can see that in 93% of those cases, this arrangement was observed. So basically, this is just an assessment of, have we ever seen this experimentally validated in X-ray crystal structures or not? And if it's not the case, or it's a little bit rarer, we can also see it here. So this part is actually very rarely observed for the red torsion here, which doesn't mean necessarily that it's uncommon. It just tells us that we should pay attention to that, and that maybe also the modeling of the ligand inside the binding site during crystallography was not perfect. What we can also let SeeSAR display to us is molecular clashes. In this case, we don't see any. And what's also pretty interesting, we can also present the unoccupied space inside the binding site, but we can talk about this in a minute. This was basically the first one through SeeSAR and its settings. The next thing I would like to do is actually to show you the binding site mode. If you would like to switch modes between SeeSAR, obviously just for the completeness, you can zoom in and zoom out with a mouse wheel on your mouse. With a right mouse click, you can swing your ligand complex, and with control and the right mouse key, you can move the ligand around, just for the sake of the completeness. And if you ever lose track of your ligand, just zoom back in with a spacebar. Now to the binding site mode. If you would like to do something inside SeeSAR, you have to switch modes. Since I would like now to show you how to increase or decrease or find other binding sites, we'll switch to the binding site mode. Now I'll click on it, and now we see the icon has changed. SeeSAR tells me that the mode is a different one now. And what you can do here, you can manually adjust your binding site by using the sequence view below. Maybe I would like to add this valine to my binding site, valine 717. For this, then I have to right-click on it and add residue to the binding site. And it will now be added, which I can see with the purple indicator here, meaning that this residue and side chain will become part of my binding site definition, which is important for docking and subsequent compound ideation steps. If you don't want to do things manually, you can also just click on this beautiful button here, which is the button to detect unoccupied druggable pockets inside the ligand. And if I now click on it, it will perform a quick scan. And what you are presented with are, as I call them, cotton candy clouds inside the binding site, which are indicators of where binding sites are available. This is the most prominent one because this is the well-known hinge binding site at almost every kinase. On the left side, you are actually presented with a lot of coloring options, which are associated with the respective binding sites in 3D. And what you can do, you can just simply click on the cotton candy clouds to add every residues inside the binding site to add them to the binding site definition. You are provided with a lot of information about the individual parameters of the discovered binding sites. The algorithm that we use for that is called Dockside Scorer, which is a very, very good algorithm to detect druggable binding sites. So binding sites that have some form of depth to them, where small molecules can bind. You're also presented with a plethora of other important features like number of H1 donors within the binding site, as well as acceptors, the surface area and the volume of the binding site, and also the hydrophobicity of the binding site here. What you can also do inside the binding site mode is to select water molecules to be important parts of the binding site. So maybe you have a pretty good idea about this water molecule here, which you can, if you right click on it and zoom on it, it's now covered by the binding site detection, but it's there. So maybe who are you? Let's label you. You are water molecule 37. And if you think this compound or this water molecule is very important and you want to preserve it within the binding site for docking and to be considered as important, you can also set this water molecule as conserved, and then it won't be replaced during docking and other procedures. But I don't want to do that now. What you will also see if you hover over the residues in the sequence view, they will also pop up in your 3D view, so you can also see where in the 3D structure you're working or are at the moment right now. And basically, that's the binding site mode. Once you're finished with adding residues or discovering binding sites, the last thing you have to do, which is really important, you have to confirm the selection of your binding site by placing the play button here. I will do it now. And now I'm finished, and the binding site has been set for every other mode out there. Now back to the protein mode. I would like to show you I wouldn't say hidden feature, but this is a pretty neat feature of SeeSAR. For this, I will switch over to the protein editor mode. For the protein editor mode, it's pretty important to know that you have to take your protein or your target structure, it can be in DNA, and add it to the protein editor mode because this is the structure you want to work with right now. The most infamous feature of the protein editor mode is actually the Sienna tool, which is hidden in this icon. And if you right click on it, you are opening a window that allows you to access the Proteins Plus server to screen for topologically similar binding sites of your receptor. So you're looking for binding sites that are very similar to what you are interested in. You can request 10 solutions per default, or if you are a little bit more braver, you can go up to 500 similar proteins. But let's just stick for the 10 and then click on search to see what PDBs have a similar binding site to the one we defined in the binding site mode. It will take maybe 10 to 15 seconds. Meanwhile, you can ask me anytime. I will have several breaks where I will check the chat for any questions from your side. And there we go. So what we are presented with right now are similar PDB structures. And you can also see where the PDB structures come from. This is always the 4-letter code of the PDBs. And what's really interesting, if you would like to compare this protein with your initial protein, you can right-click on it and add it to the protein mode. In the protein mode, I will now color both my proteins in different colors. This one remain blue, and this one will now become a beautiful, what's the color? Eggplant. Let's call it eggplant. And what you will see here is now that molecules are superposed, obviously. And if I now click on the show binding site only the residues that I defined in the binding site mode will be lined up. There's also a possibility to align your proteins. So if you have two different protein structures, which can also be an in-house structure, you can trace on the 3D alignment of binding sites. And SeeSAR will then tell you that the protein binding sites were successfully aligned and superposed, which will also result that the sequences will also be aligned accordingly. What's pretty cool, a feature that not many people know, is you can actually check for differences in the binding site within SeeSAR. It's namely this hide components with similar conformations. And if I now click on it, I will be requested with a threshold of an RMSD value, which I can now increase to spot differences in the binding site. So if I now go up to 1 angstrom, residues that are no longer similar to the binding site will disappear. And now that residues that are dissimilar, will disappear. And maybe let's take a look at lysine here. And I can see here that SeeSAR tells me that those both have an RMSD value above 1 angstrom, which means I can therefore collect knowledge about highly flexible residues and side chains within my binding site to pay attention to dockings where I say, well, this binding site may be a little bit unsure, maybe blocked by a lysine or so. And this feature is also pretty interesting if you have somewhat very similar targets to address selectivity issues. Kind of like spot, okay, is there room in one structure or another after I perform my docking to also spot differences there to act accordingly depending on your case. What you can do in the protein editor as well is load a structure there and then modify it based on your needs. So maybe I would like to play with this lysine here. I can click on my lysine and maybe add a methyl group here. So basic modifications of the binding site can also be done. Sometimes it's kind of like also interesting to maybe perform some sort of computational mutagenesis studies to check if there's enough space for phenylalanine or rotate stuff. So yeah, actually pretty rudimental, but it's kind of like can do a little bit of things here and there. Okay. Let's remove this structure here. The last thing I would like to show you, so basically you can color your protein with these features here. Maybe let's make it blue. And if you go down to the protein surface here, which was introduced in SeeSAR 13, is the possibility to actually add surfaces and color surfaces within SeeSAR. And if I now click on the protein here, the binding site will pop up. And I can also adjust the binding site to be transparent or not, as well as color it according to log p values of the residues, as well as elements or even chains. You can also decide for a color of your binding site. Maybe I will just go with something more flashy. And also it's possible to show the whole protein surface, namely here. If I now click on the show whole protein, the whole protein surface will emerge once it's calculated, which takes a few seconds. And I can also color the protein surface accordingly. And binding site orange. And yeah, that's basically it. The last thing I want to show you before I finish this sequence is actually how to export the 3D structure of this protein to PowerPoint or as a 3D model. For this, we go to Utilities and select the last thing, namely the Export 3D Scene. I will just quickly drop it somewhere with Workshop Hello. And now I will go to PowerPoint and add just a empty slide. And by going to Add 3D Model, I will go to the section here, select my GLB exported file from SeeSAR, and add it to PowerPoint. And what I really like about this one is actually that you can rotate it. What many people struggle with to see, but once they see it, they cannot unsee it. We also export the height spheres together and alongside with a 3D export, even the water molecules, and also the torsion colorings. So you can also do a lot of crazy stuff here. You can also add animations like a little bit of churning. And if you go to presenters mode, you can also make it very interactive and also do a lot of stuff with it. Sometimes you also share 3D structures on Microsoft Teams, which supports the GLB file system. It's a lot of fun, to be honest. I really also love the possibility to actually export the colors you need or you like. Okay. Did I forget anything? Doesn't seem so far. So basically, this was the first part for XPO. O like the number. And if we now go through the ligands, we define the binding site, and this is actually what I would like to use now. I will now select my ligand, confirm my binding site. Since my ligand is pretty small, it's a fragment binder, unsurprisingly, I would like to extend it a little bit. So I go to the binding site mode, check for potential larger binding sites. I got one, which is now in my eggplant color. Now it's more raspberry now. Confirm my selection. And for the next miracle, I will take my ligand and push it into the molecule editor mode. By doing so, I will now have my ligand in front of me with the protonation, with all the hydrogen atoms present. And what I can do now, I can modify my ligand. So for very basic ideas, I can just click on one heavy atom and maybe change it for nitrogen to check if this substitution actually affects the binding affinity. Once I'm done, I have to export my molecule to the table. And I see, well, nitrogen is somewhat tolerated in this region. What we also see now, once I leave the protein mode, I will also get information about the hydrogen network within SeeSAR. And what this hydrogen network actually does, it also tells me how great the geometry of my complex actually is. So the deeper the color, the more darker green it is, the more optimized the H-bond arrangement between my ligand and target actually is. So if I have like very light colored greens, like maybe this intramolecular H-bond between the carboxylic acid and the backbone here, I can actually see that the arrangement here is not completely perfect, and therefore the color is a little bit lighter. Back to the molecule editing, I can also just introduce new groups here, like a carbon atom. Let's see if this is tolerated. And yeah, it's also tolerated. You will also see, if you browse through the results, that sometimes it adapts a little bit. This is due to the fact that you also perform a small optimization step to kind of like see if the no modification really suits the setup or not. So basically, this is just the molecule editor mode where you can play with your ligand a little bit. You can also, if there's anything that I use the hotkeys on my keyboard to introduce a new element, but you can also go to change element here. So if you would like to go with something from the periodic table, so these are the atoms that we support, but this is basically also the atoms that are most frequently used for medicinal chemistry approaches. You can also change it for iodine. Let's see if this works. Yep, it works. It's also directly assessed. What I really like about the whole concept, maybe you saw it, if you change the atom type, the bond length is also automatically adjusted to obviously make it scientifically valid. There was a question about changing the protonation state of your complex. It's possible here in the molecule editor mode. So you can just click on this nitrogen. And if you feel like this nitrogen should absolutely be protonated, you can change the protonation step either here, increase charge, or you can do it with the hotkeys minus plus. And now let's see if SeeSAR is happy about this protonation state. And it's not that much, but this is how you can actually adjust the protonation state of your ligand in an area of your ligand. And here, this is how you perform molecule editing in the molecule editor mode. For my next step, I would actually like to introduce you to the docking mode. Docking is very, very, very easy in SeeSAR due to two reasons I already mentioned. One reason is that we have already the binding site defined, so everything is done automatically inside the binding site. The second factor is the protonation. So if we do docking within SeeSAR, we consider everything from tautomerization to protonation states of the ligand inside the binding site. So therefore, there is no need for us to additionally prepare the ligands as it is required in some other docking protocols or docking software. Once you have your ligand inside the binding site, you just have to decide for the docking. And in this case, we would just to perform very standard docking. So basically just docking with one compound. And this is the standard docking button. If you push it, it will start with the calculations. So let's give it a few seconds. And then we are presented with the results, which you can check here. And if you just go through them, you will see what happens. And sometimes you have obviously candidates that are not so nice. What you will see here is actually, if I now use this bar to go to the right of the table, I'm getting a lot of information here. We call it a traffic light scheme that gives you ideas about how satisfied you should be with your prediction. You get information about the torsions. So if no torsions are available, no torsions are discovered that are high energy conformations, you are faced with green torsions. And you also check for intra and intermolecular clashes. So you get a nice scheme here. Now everything is green, so it's a little bit boring. Another feature that you can do here in this window is actually to rank your compounds. And if you do it by clicking here, and you can see that now my compounds are arranged. This is the best prediction here. And you can also see like the range of the height estimation. We provide always, we calculate one value for height, and then add 2 orders of magnitude towards as error bars, more or less, to give you a better assessment, because obviously the scoring is not perfect, no scoring algorithm is, and it better reflects the biological insecurities inside the docking score. The question would also be like, okay, this was one compound. How do I use my own compounds for docking? Pretty easily, to be honest. You just go to SeeSAR, and then to the menu, you can select the load molecules. And I will just select a small selection of compounds. like small hinge binding motifs here and there, nothing special. And by simply pushing standard docking, I can dock my compounds inside the binding site. And there we go. 10 compounds docked within, how much was that? 10 seconds. They are also already ranked. I can also just rank them according to their name. But now I'm excited for the most promising compounds. And let's check them. You can see very interesting. And now I'm also receiving more information if there is anything wrong with my complex or if I should double check something here and there. So basically, this is how you stay in complete control of your results. We provide you with very easy and very visual assessment of your complex, so you can decide if you believe the complex or not, which is very important to select the best compounds for pursuing anything further. What's also a possibility within SeeSAR, I will now just remove this result, is to perform actually template-based docking. If I select my compound and I feel like this is actually the way to go, and I would like to all of my compounds to be very similar, to express similar binding modes of the substructures at the binding site, you can set this compound as a template, which allows you to perform template-based docking. For template-based docking, our ratio is to align at least 5 compounds based on their substructure matching to the binding site. You also maybe have noticed that it's way faster compared to standard docking because we also provide additional information on where the first fragment has to be docked. So template docking is 10 times faster compared to standard docking. And this is how you can also accelerate your visual screening approaches, or if you have a series of compounds and you have a pretty good reasoning about one binding mode, you can use one compound as the example and then align all the subsequent compounds to your compounds afterwards. And you will see that in most cases, we kind of like fulfill this hinge binding motive of the hinge binding of this other endo here, which is no surprise due to the fact that it was template-based docked. Covalent docking is another topic. I won't talk about this now. I can show you one example later on. Before I will start with the next section, I will show you also the analyzer mode. I will just pick my generated poses and then transfer all of them to the analyzer mode. So the analyzer mode is actually what we use also internally, obviously, to do the visual assessment of our compounds. So every time we do a visual screening at BioSolveIT, we go into detail to double check everything and to select only the best compounds. And for this, we use the analyzer mode where we have a good overview on everything. The beautiful feature of the analyzer mode is actually that I can group molecules by clicking this button here. And if I do so, only the best scoring pose of my compound will be shown to me. Apply the filter. And from the 6 compounds that we were able to dock with the template-based docking, we see now only the top scoring ones. So basically, 2 of them are pretty nice. What I can apply here as well are actually filters. So let's assume I would like only to have only drug-like molecules or lead-like molecules or fragment-like compounds. Those are preset filters that you get information here. What filters are applied here? But what I would like to do now is actually to screen for only compounds with good torsions. So I now apply my filter, and I see that the table has changed. I'm now facing only compounds with green torsions, so no high energy conformations. By now, I can expand it with whatever I want. I can also check for only green intermolecular clashes. I can set my own my own parameters like molecular weight. I would like only to see stuff with only 500 Dalton or less, and so on and so forth. So everything that you would consider to be a filter criteria can be used and applied here. And voila, only the best surviving compounds in this field. What many people don't know, you can also do a little bit more of a fancy assessment here, namely the grid view. You can switch to the grid view on the right side of SeeSAR, where you can also adjust the net scheme, net diagram here. You can also add own properties, like I want only a particular number of hydrogen bonds to be present. This is a pretty nice feature if you would like to support, if you check for several parameters for optimization, and you can feed anything that is part of the SD file as part of the property plot settings here. So every time something is an outliner, it will receive a red score, a red dot, and then you can just browse through things here and you will spot, this one is not perfect. So especially if you have like very many parameters you would like to consider, this is a pretty nice feature. Also something not many people know is actually the possibility to couple biological data with the calculated delta G values, so the free energy. But for doing this, you can just click on this performance check. You can select the molecules. You can add your experimental values by just providing the associated SD field inside the file. And then you will also receive a performance check of how the calculated values actually match your biological data. Anything else I would like to mention about the analyzer mode? Oh, yes, obviously I do. You can also obviously fix molecules. So maybe you would like to keep this one visible when you do a virtual screening to kind of like check for arrangements of hydrogen bond donors and acceptors and so on and so forth. You can then pin your molecules. You can also mark them as favorites, which we do for selecting candidates to follow up with. You can also type in annotations like ra ra ra, and then save it for the future. You can also actually save the perspective of your ligand. Like if I now press Capture C, and then I change the whole scenery, which is very useful for publications, to be honest. I can now go back to my adaptation and restore the scene, and then it will be exactly in the 3D arrangement that I saved it as. So I had many occasions where I had to redo a lot of figures because something was missing, and then I had to set everything up back during my PhD. So I really appreciate this feature a lot. You can also mark your molecules as active and inactive, which is kind of like very helpful if you work with a set of compounds. To kind of like keep track of what you like or what you don't like. And also you can color every single molecule based on your needs, which is also kind of interesting if you would like to group molecules here and then. The question is it possible to extract the tables? Yes. To make it very short, if you would like to extract the tables, you just select whatever you would like to have. Now I have only the best candidates. I can also turn off group molecules and just turn off every single filter here. So everything is now back where it's supposed to be. I can check everything. And then if I go to the export button here, the save disk file, you can select several, you can select up to 2 forms how to export the molecules. One is the SD format, which also contains everything that is inside this table. It will also contain the numerical value for the upper and the lower predicted binding affinity, so a numerical value for the binding affinity. It contains also all kind of stuff that you calculate. And obviously, you can also export it as an Excel sheet, which will also include the 3D representations of the molecules, including SMILES files. So this is kind of like the way to go for whatever you would like to do with them subsequently. So yeah, it's possible to do so. Something I maybe haven't mentioned yet so far, we have a pretty long run collaboration running with Optibrium. So if you have an Optibrium license, it's also possible to calculate the Optibrium properties within SeeSAR by selecting the compounds and then selecting Optibrium properties. And what you will get is actually, I have to expand the table here a little bit, are the highly requested and very popular ADME properties of Optibrium. I mean, you know them as much as I do. You can select whatever is of interest to you. And then if you click on the parameters that are of interest to you, they will be added to the table. And then you can obviously check them for whatever you need at the moment. So they can also be exported as SD file, columns, entries, and also as Excel sheet. Again, for machine learning approaches, you name it. A little bit of water. Because my voice is starting to break down. So I would now step towards the inspirator mode. So I'll just go back to my protein and select my fragment and add it to the inspirator mode. The inspirator mode is my favorite mode inside of SeeSAR because there's so much you can do with the inspirator mode. The first thing you can do with the inspirator mode is the latest addition to SeeSAR 13, namely metachemesis. It's a play on medicinal chemistry and mutagenesis because you mutate a ligand. And it's called analogging here. So what you're doing here, you apply 290 medicinal chemistry transformations, the most common ones, on your compound of interest to check for smaller modifications that can affect the binding affinity. A beautiful thing to do to create a series of compounds and kind of like to play around with potential ideation steps. And what you will receive are suggestions. So maybe I do this hydroxy group here, add an amine there, fluorine atom. We also perform ring modifications that I really, really like to just check where potential optimization is possible for ring systems. You get the idea. So now these are only 10 results. If you're interested to have more results, you can always adjust the parameter settings here. The default for most modes of SeeSAR are actually 10, but you can go up to 500 if you'd like to. The most beautiful part about metachemesis is that you don't have to think about what transformations are used, and we don't enumerate stuff that is doomed to fail. So basically, we would never show you something that ends up as a clash with a binding site surface, because obviously there is no need to check those kind of things. So it's kind of like, it looks pretty, yeah, I wouldn't say boring, but the finesse is actually how it only shows you results that are somewhat reasonable to pursue further. So there is no need to add a carboxylic acid at every single position and then dock the compound and check, will be there space or not. This samples the whole chemical space around one compound so much more better and so much more efficiently. Yeah, this is metachemesis. I will remove the results of metachemesis because I will now go through several ideation steps so we don't get lost. In my next miracle, I would like to show you fast grow. If you set an exit vector at your compound, you will see that this green little fella here starts to glow up. And this little fella here tells you that FastGrow is available. Per default, FastGrow screens a library of 12,000 smaller fragments. Maybe just click on it once to see what happens. Now I'm screening 12,000 fragments for the best candidates to complement the shape of my binding site. Once the library has been loaded, you see I'm now sampling 12,000 fragments, and of each fragment, 10 conformations. So basically, I'm going through a catalog of 120,000 possible modifications to find the best complementing solutions. Again, nothing that will lead to a clash with the binding site is shown to you, and it's driven by actually interactions within the binding site. And those are the results that you will see there. So basically, just a compound ideation process to see if there's something that you would like or not. And that actually kind of like really nicely complements the binding site. What I really do love about FASCO is actually that it also shows you potential interaction partners within the binding site that you would have considered otherwise. Maybe let's go through. I see also kind of like interactions here of my cyclic amine. So kind of like projecting towards the binding site. It's pretty neat. An important information for you on our website, if you go to the SeeSAR page and then to fragment files, you will also find an even larger library of 120,000 fragments to sample from. You can download them, and then you have a larger variety of fragments to use within SeeSAR and the Inspirator mode. To load this database, you go to System Settings and then Inspirator Settings, and then you can select the database you want to work with. Again, 12,000 is the default in SeeSAR, and once you've downloaded the 120,000, you can just use them to ideate. If you don't like what you see, sometimes this happens, or you just want to have more is always better, you can just adjust the number of solutions. So I'll now go up to, let's be greedy, 100 solutions, and click. And now again, just to show you how fast this is, I'm working with 120,000 now times 10 because 10 confirmations. So I'm sampling 1.2 million for the best shape complementarity in the binding site within seconds. This is huge. This is very, very fast. So a lot of ideas how to actually optimize a compound, but if you rank them, you can actually see how you kind of like really push the whole compound to better binding affinities. Yeah, this is how you use FASCO. Now you will notice that there is another button I haven't talked about yet, namely this define from for button. Maybe I will show you how to use it in a very interesting way. So I just go with this compound for the time being, push it to the Inspirator, remove everything else. And what I would like to do now, I will actually keep the right part of my compound and use this to grow into the hinge binding motive site. What I will do now, I will use pharmacophore constraints. So since I know that hinge binders actually have an H-bond acceptor in this area, I set H-bond acceptors on this particular constraint, and then I will set one constraint in this area, and this one is actually a donator. So what I do now, I will again use FASCO, but to check for better substitutions in this area to actually fulfill my hinge binding motive. Again, I will request 100 results, and let's go. Almost there. There you go. And now if I click on the results, some are, let's phrase it, interesting, but it's completely up to you to decide if you like them or not. And sometimes we also get nice ideas how to actually complement the binding site with new hinge binding motives. So actually, I really like FASCO potential because you can do so much with it, from scaffold hopping to actually fragment evolution. Again, an okay-ish hinge binding motive, I would say. Sometimes it gets a little bit wild with rotatable bonds, but this is something that you can filter out subsequently. And you see quite a lot of ideas to work with. Okay, this was faster. Now to something that we get asked quite a lot. I'll clean the inspirator mode now. The question is how to actually link two fragments. I will also remove everything here and just load two molecules. Load, and I have a sample prepared, merging. So let's assume you have two fragment binders, or even like two motors. One is like this, alpha indole, and one is like this. And you ask yourself, well, is there any way to actually connect both of them in some way, in a sophisticated way? To do so, I have to select both of them, and this is a very important step. To merge two fragments, I have to load both simultaneously to the inspirator mode. Now I will transfer those both to the inspirator mode. And now I will decide how to actually connect them. For this case, I will select this hydrogen atom as the exit vector and this one as the exit vector. So in this case, I'm searching now for a substitution between those both fragments in one way or another. You will notice that linking and merging became active because it's green. And if I now press on it, I will check for 3D replacements within the binding site by using our recall algorithm. It will now take some time because I forgot to set it down to 100 to 10. Now I'm getting 100 results. And again, you see the speed of the whole process. And what I get now are actually a lot of ideas how to connect both compounds. What I really like here is actually that I'm also receiving information about additional projections toward the binding site, so how to complement the binding site here. And again, a very beautiful compound ideation mechanism. Just so that you know, you have to actually download the recall scaffolds, so the recall 3D coordinates. They are available on our website. I personally prefer the PDB index because it's based on experimental data, co-crystallized fragments, compounds, and they are very MedChem-like. But we also have other indices available, like compounds from the Zinc database. They're also from the Cambridge Crystallographic Data Center, which requires an additional license from their side. And also for very interesting compound ideation ideas, Peter Ertel's Magic Rings. There's a beautiful publication out there, which is also linked under the recall index. Another thing that people don't always know, I will again remove everything here, and also maybe reduce results so that we don't calculate everything 2,000 times. I'll reduce the solutions. Sometimes recall gives you a lot of very flexible results. So many rotatable bonds that I personally don't like. You like it as well. So kind of like avoid this kind of situation, you can use pharmacophore constraints. So I just define a new pharmacophore constraint and place it between those both heavy atoms here, here and here, here and here. Set sphere to center in between them. And now I can apply pharmacophore constraints of my choice. I like to use ring atoms in this area, but if you have something very particular in mind, you can also use your own smarts, which also includes the definitions of particular heavy atoms inside the ring system and so on and so forth. So also a very valuable tool. I will click on ring atoms, and now let's check if we find something to connect those two fragments in the best possible way. That is also not that flexible. And actually, I get ideas like that, ideas like that. So basically, this is also how you can fine-tune your results a little bit. Very important to know, obviously, pharmacophore constraints can be applied in almost every mode of SeeSAR. So this also includes the docking mode, this includes the inspirator mode, this includes the analyzer mode. If you would like to filter your docking results based on interactions with the receptor binding site, just go with the pharmacophore constraints, and every time there's need for you to adjust the number of solutions, use the parameters. And this goes also for the docking mode. Maybe just to clean things up. If you have compounds in the docking mode, you can select a lot of parameters like number of poses, but also work with the clash tolerance, which reduces the binding site surface. So if a site is very, very tightly defined, you can increase the clash freedom here by going to high clash tolerance. Also, per default, we only generate the lowest energy conformations of aliphatic rings, aliphatic 6-membered ring systems. If you feel quirky, you can go also up to the higher energy both conformations or the twist conformations. I personally will stick with a low energy conformation ring. So ligand-based drug discovery is also the case. It's always the case, not always, but quite often when you don't have a crystal structure available, but you have a known binder flying around somewhere from a higher throughput screening or as reported in the literature, and you just want like to find something that's kind of like similar to the ligand. For this little example, I will now load a few molecules. So basically, to add molecules to the similarity scanner, you can just load the molecules inside the similarity scanner itself, or push molecules from another mode to the similarity scanner. And you only need two things for the similarity scanner, namely one template ligand and one other molecule. So this is here my made up ligand that I just draw randomly. And I will now use this ligand as a template and align 99 other ligands on my ligand as well. If I just kind of like go through each one of them, you will notice that they're kind of like similar, but not completely. Sometimes the ring system is coupled to a phenyl ring system. Sometimes it's just rearranged. So it's not completely the same, but you kind of like, you get the vibe. It's close enough to being what your ligand looks like. And my question is actually, well, I don't know if any of those ligands is somewhat similar to my query compound. And now what I would like to do, I would like to align those ligands and also have some form of numerical value to kind of like rank them. So a ligand-based virtual screening or a ligand-based superposition of my ligands. Once I have selected my template molecule, I can now again adjust the number of poses that I want to generate, my minimum similarity rating, and also the allowed ring conformations. And I could also again apply pharmacophore constraints I would like to. And once I'm done with the whole setting part, I can simply start my similarity scanner run. Again, I would say it's one of the faster algorithms out there. Right now, I have one compound and 99 molecules, and it will take us maybe close to half a minute. You can already see we have reached already 27%. So it's very, very fast. I think it makes sense to kind of like talk about it once the one has finished. Now we're struggling, but almost there. Yeah, there we go. So based on our similarity score of 0.6, 64 compounds were not aligned on our ligand, which means they would have a pretty low similarity. If you still would like to see those results, you have to adjust the similarity rating below to come to a conclusion. Again, I have the possibility to rank my compounds by clicking on the similarity rating. And what I would like to do now, I will set my initial compound as tagged and give it a different color so that we can all compare the results. I think maybe blue. Yeah, this will work for us. So, and now I have the possibility to go for my compounds. So basically, I'll just tell you how this whole procedure works. In ultimate theory, I'm trying to match volumes as well as H-bond acceptors and donors on my query compound. So if I now zoom in on my compound, we will see that it tries to kind of like match molecular features based on their 3D shape. What I can see now tries to kind of like satisfy the lipophilic tendencies here, but the real beauty happens actually with the H-bond donors and acceptors. So in this case, we have the imidazole in this area, and now it tries to match this these heterocycles to this 5-membered ring system. Because the things work, I have an H-bond acceptor in this area, like this double bonded nitrogen here, and this nitrogen here will also has hydrogen bond donor properties. So it tries to align them accordingly. Same also happens for this keto group here. So it kind of like tries to match the geometry. And if we also now check the geometry of this little fella here, we can check that this both features, so the blue dots are actually H-bond acceptor partners, H-bond donor partners for this oxygen here. And if we check now with this little fella here, we see that kind of like tries to align those interaction hotspots on my ligand. And it does it for the whole ligand system. So again, here also, we see this nitrogen here, H-bond acceptor, and it tries to match it with this oxygen here, while also maintaining the shape complementarity of this area. And yeah, this is what happens. Sometimes you get also kind of like very unsurprising solutions, like in this case. Still, you can also see the matching here. It's not completely obvious, I would say, but it tries its best to kind of like align those molecules. To give you another idea, clear similarity scanner. This is one of an older projects, but it's interesting to see the potential behind this one. So this was a drug candidate that I used as a query compound and selected some compounds from our other technology, Infinity. And I was asking myself, well, is there any way to kind of like enrich my sources? So the way I perceive the similarity scanner is an orthogonal method that can be coupled to your virtual screening approaches. So basically to check if my compounds also match in 2D, or basically it's now in 3D, but ligand-based. This is also a variable factor that can be added to the information in compound selection process. So now I'll define my query compound, and you will see now the structures are pretty different compared to my initial structure. Let's color it again like this. And if I now start my similarity scanner, my 3 compounds will be aligned. And there we go. You see my structure here. And what I really love about this one is actually the scaffold hopping perspective on this one. So you get the matching of this molecule here, and you would never imagine them to be kind of like somewhat similar. But if you browse through the results, you can actually see how it tries to kind of like match properties like here. This hydroxy group as an H-bond donor, H-bond acceptor in this area. Here, the ring system that kind of like tries to match as per the parameter here, the hydrogen bond acceptor way. You can also go a little bit lower to the other structures. And you see here, beautiful. Right? So a lot of potential here. It even, you would never imagine the kind of like, you have this morpholine ring system here. And I would never consider that an amide could be some sort of the same 3D shape and also kind of like fulfilling the same role. We have an H-bond donor in this area, and in this area we have a hydrogen bond acceptor. And kind of like, now you get the vibe that it can be a substitution pattern here. Reasonable bioisoster or somewhat bioisotonic here. So you see, there's a lot of things you can achieve with the similarity scanner, but it's completely up to you how you utilize it to the fullest. There are some questions with regards to the similarity scanner. The question is if the molecules are rigid during the sampling. The template is rigid. So the one you decide to use as a template to align all your other compounds on, this is rigid. The rest is used as flexible conformations. So everything is considered during the whole process. Okay. Now I will switch over to the last miracle of the session, namely the covalent docking part. I will restart everything. And you also see my voice starts to break apart. So now for covalent docking, I picked 8F2C, a small, beautiful SARS-CoV-2 main protease structure. And the first thing you will notice about covalent compounds is actually that the covalent compounds are presented a little bit differently for their estimated binding affinity. This is maybe one reason because it's close to impossible for us to assess the contribution part of the covalent bond that is formed during the whole covalent docking procedure, or the covalent binding event. And therefore, let's be honest, we just ignore it. And since we cannot assess the overall delta G resulting from this binding event, we just represent it as an open end in regards to the binding affinity, because it can be such a huge contribution. Therefore, we just kind of like phase it out. Yet we obviously contribute, as you can see with the height values, all the other contributions of the atoms, which is also the driving force for our ranking. Once I confirmed my ligand, I define the binding site. And for covalent docking, it's actually pretty straightforward. I use my ligand, transfer it to the docking mode. I can also add more ligands, but I will talk about that in a minute. And to perform covalent docking, I just need to select the residue I would like to work with. If there is only one already covalently recognized structure, I don't have to do anything. If I have several available, I can actually select and deselect them. And the one that is highlighted in purple is the one I would like to dock my compound to. Once I have everything set up, I can just push covalent docking button and generate no results. And there you go. 10 poses generated. I can again rank them. And I can also superpose my compounds so that you can see the RMSD value will be close maybe to 1 something. So a pretty decent covalent docking from my perspective, and I think from yours as well. If you would like to use covalent docking on a series of compounds, it works basically in the same way. You load the molecules, covalent docking molecules. And these are my covalent compounds. One thing that's very important for the covalent docking, my covalent compounds need an attachment point to be used. So you see this R, and this R is part of my ligand. So basically, the way I dock my compounds in covalent docking is the bound form of my ligand, the form that is bound to the residue. So in this case, this is a Michael acceptor, or it was a Michael acceptor. And during the binding event, this double bond disappeared and formed a connection, a covalent bond to the sulfur atom of the cysteine here. So this is how we approach the covalent docking, by using the ligands in a transformed state. You can do it manually in the molecule editor mode, or you can also use our 9 workflows to introduce, to transform SMILES or SD files of your choice into the covalently bound form. So once you have your compounds loaded, you see everybody wears an R tag to that. You can just push the covalent docking button. And I'm presented with the results. Obviously, the co-crystallized fragment is on top, but I also receive ideas about my other compounds as well. Yet again, I can export them, push them to the inspirator mode, and just group molecules and then check for the best positions of each one. Yeah, and this is very easy for covalent docking. We also have an extended covalent docking tutorial available on YouTube as well that addresses a lot of questions, but I think it would be going too much into detail for now.